Hello everyone, I am Kunal and I welcome you to Hollywoodfysik. I am a PhD student at Stockholmsuniversitet in the physics department. I work on experimental physics, particularly in the field of astroparticle physics, in which we are looking for particles coming from space. So today I'll show you the joy of physics as is experienced in movies. So we'll discuss how people and creative artists use the make of physical laws, or maybe do not make the use of physical laws, and show them in movies. So there are a lot of questions that we get when we are watching movies. I'm sure you must have also realized that when you're watching a certain scene, something about it just doesn't make sense. It does look good in an artistic manner, but maybe there is something which is not really physically possible. So one such question that recently occurred to me when I was watching a movie is, what happens to a human being if he gets exposed to space without any spacesuit? So when you have all these movies like the Guardians of Galaxy, Gravity, The Martian, etc., which show scenes when humans go into space and suddenly the spacesuit is removed. So what do you think will happen? Any guesses? Usually the guesses that we get, or the basic guesses that we have, is either the body will explode because space, absolute space, almost has zero pressure. So if you don't have any pressure, you might explode. Okay, that's a fair guess. Then the second one usually we get is that you may freeze to death. Absolute space has almost zero Kelvin temperature, which is really low. The normal room temperature, for example, is like about 300 kelvins. So we are talking about a temperature almost close to zero. So you might freeze to death. Or the third option is you'll suffocate, because as we know, there is no air in space. So these three things all might be the case, but our question right now is which of these options might lead to your death the first. So let's first watch how it goes in the movies. So we have a scene here from Guardians of Galaxy Volume 2, and in that they try to depict what might happen. So let's just have a look how the directors tried to show this.
Don't be ridiculous! Get back into your pod! You can't fit two people in there, you're gonna die! You'll die in seconds! Quit!
So we saw in the last scene that the protagonist went out, took out his mask and gave it to the other person, and the sidekick said that you might die in a matter of seconds, and that is because he won't be able to breathe. You can also see that the directors tried to show his face when it started to freeze. So he might die due to freezing, or he might die due to a lack of air. And there is also the third option, that he might explode. However, in that scene they didn't exactly show that. So what will really happen? Will he really die in a matter of seconds, or will it take a bit longer? So as physicists, we are trying to approach this through the method of experiments, and we'll test our theories and check them with experiments, and that's how a physicist tries to solve problems. So the first approach, will he freeze to death? So there are different levels of temperatures on this planet. We have extreme cold places like Siberia or even some parts of Sweden, and then you have some really hot places like the deserts in Africa or even India. So we know that the body can withstand different levels of temperatures, and it absorbs or emits heat depending on where it is. So in space, we would radiate heat in this manner, and this is the law which tells us how it will be so. So the power by which we radiate heat depends on the energy that is being released per time, and that depends on these three terms. As you can see, there is a coefficient of proportionality, and the surface area of our body, and the temperature difference. And according to this law, this power depends on 4 to the power of the temperature difference. So it depends a lot on the difference in temperatures. So it takes a very long time for the body to cool down in space. But how do we know that? We approach this with this particular equation. So imagine this potato to be a human, and the surface area for this then would be about 2 meters square. We can assume that the entire surface area of the human skin is close to that. This is a fair approximation. And let us assume that the temperature of the body is close to the room temperature, let's assume, and that's about 300 kelvins. And just to go from the room temperature to absolute zero, the temperature difference would be 300 Kelvin. So when we put all these values in that particular equation, we see that the power comes out to be 900 watts. But we don't really understand the concept of watts in daily life, right? So we try to understand what does 900 watt mean, and we do this by taking another expression that we know that energy is, we can write it down as mc delta T, where m is the mass of the particular body. C here refers to the heat capacity of that particular body. It says, it translates to like how, what is the efficiency in which we are absorbing or releasing heat. So here it says that we do that with 4 kilojoule per kg per Kelvin, and it's all like just equations. We just put things into that, assuming a 70 kilogram person, and the delta T, just to see how much it takes just to change the temperature by 1 Kelvin. We see that the time to cool down in space just by 1 degree is about 5 minutes. And in order to go to a temperature where to reach absolute zero, it will take a long time. So the time limit imposed by freezing of death is of the order of more than 5 minutes for sure. So this is the first assumption, will we freeze to death? Now let's see the second one. The body explodes. So we know that the human body can withstand different levels of pressure. We know that in the high mountains the pressure is low, and we can still feel okay, if not exactly comfortable, but we can still survive in those temperatures. And for those of you who have done deep sea diving, you know that once you start to go deeper into the water, also for those who have been swimming in the deeper end of the pool, you do realize your body recognizes it when you start to have more pressure. You can feel your head aching and things like that. So however, it doesn't kill you, right? So we know that the body can go to certain extents of pressure differences. The pressure at the top of Mount Everest is about 1/3 the atmospheric pressure at normal sea level, and in diving it can go really, it can be a lot, as much as 25 atms. So we tried to perform an experiment. We tried to simulate how it would look like in the laboratory. So when you expose certain things to vacuum. So what we did is we took a glass jar and we put certain objects in it, and we slowly started to take out the air from it. So slowly it started to develop some sort of vacuum, and there were 3 things kept in it. There was a glass with some water in it, there was a cookie, and there was a core. So the core was kept there to simulate the closest thing that we can have to a human skin. It's not it doesn't have the properties exactly like that of a human skin, but it is an approximation. So having said that, and with that particular approximation, we start to pump out some air. So we are taking out some air, and as we proceed, this second photograph was at about halfway through when the pressure was really low, and then you see that the cookie starts to expand. It really goes berserk, and the water is still like that, and the core still looks okay. Now we started to pump out a lot more, and when we reached almost vacuum like state, you see that the water starts to boil. So that is another effect. So when we are talking about boiling of water, we say that the vapor pressure of that particular liquid is equal to the external pressure, and since there is no external pressure, it doesn't the vapor pressure is equates to that, so it starts to boil. And this is what will happen in absolute vacuum, that your liquids will simply start to boil, and the cookie is going crazy because it has a lot of pressure on the inside, and the chocolate layer is not strong enough to control that, to keep it in place. However, the curve was still intact. The reason for that, although there is no pressure outside, but the skin is strong enough to withstand the incoming pressure from the inside. So we see that the pressure will most likely not make us explode. We might have some capillaries which will expand a bit, and it might be really uncomfortable when that happens, but at least we will not explode in space. So this takes out the second option. So the third option remains, that we will suffocate, because the human body cannot live for more than about the order of few minutes, and if without air, and if we don't get air, if we can't breathe, we will suffocate to death. In reality, all these three things will be happening at the same time, so the situation will be a bit more complex. So what will really happen in space? It will be a combination of these things. So for our result, we conclude that we would survive only few minutes in space, and then we'll suffocate to death first before being frozen. What we saw, that this is not really possible in the movies, and there are a lot of other scenes in which we do see science being respected and followed, but sometimes people like to be imaginative, and that allows for movie makers to make certain scenes. But as physicists, we know what is possible and what is not, and this is also part of the fun. As physicists, you often enjoy the movies in a different manner, and it's to realize more such fun, we would encourage you to come and study more physics and start a very happy journey with us. So thanks all.